So I'm going to talk about sort of a more amateur approach to FRB observations than Wolfgang described, even though I guess his radio telescope is notionally run by amateurs. It's just a whole lot bigger and better funded. So I'm the current president of the Canadian Centre for Experimental Radio Astronomy. We started it as a federal not-for-profit in 2016. It was housed for several years at a place that none of you will know about, called the Rita Regional Center. And then in 2021, we were forced to move to a new site, politics mostly. So we now are primarily set up on a 38-acre cleared site near a town that, again, none of you will have heard of, called Rideau Ferry. So our mission is kind of loosely defined. We engage in small-scale research activities. We develop tools and techniques to support small-scale radio astronomy, which includes both amateur radio astronomy and programs at smaller institutions, undergraduate programs to introduce students to radio astronomy, that sort of thing. We've in the past partnered with academic institutions in support of undergraduate astrophysics. Carleton University is one of them. Because of COVID, that collaboration is currently no longer in place, although it may come back again when the corresponding program, sort of leaps back to life. So we had to move. So we spent a lot of the spring, summer, and fall of 2021 pouring concrete and putting in dishes, and the trailer you can see there. So that's the inside of the trailer. There's a stack of receiver equipment and computers and so on there inside the trailer. And what we're mostly focusing on at the moment is FRBs. So this talk should, dovetail somewhat with Wolfgang's talk. We decided that since we weren't doing the observation program driven by Carleton, we wanted to find something that could contribute to actual science, which is unusual for amateur scale radio astronomy. And I'll talk about that in a minute. So FRBs are fast radio bursts. They were more or less a newly discovered phenomenon, first detected in archival data by Lorimer and Markovic around 2007. Origins are still not positively identified. Black hole mergers, magnetar outbursts, very large supergiant pulses from existing pulsars that we don't know about. So their ordinary outbursts would be too small for us to see, and then maybe they, for whatever reason, because they just swallowed a whole bunch of mass or something, produced these extra giant pulses. We don't really know for sure. Some of them we are now kind of converging on the magnetar explanation, but that would not describe, the vast majority of them at this point. They're brief, a few hundred microseconds to perhaps a millisecond or two in duration. They can be very bright. The burst observed by STARE-2, which is what Wolfgang alluded to, had a peak flux of greater than 1 million Jansky. They're mostly highly dispersed, which implies that most FRBs have been assumed to be extragalactic due to their high apparent dispersion measure. The one that STARE-2 observed, of course, is actually within our galaxy. About 30,000 light years away is the number that sticks in my head, but don't quote me. They're distributed more or less uniformly across the sky. There are some statistical exceptions. M81 appears to be a popular emitter of FRBs. About 90% of them are singletons. They never repeat, or at least at the time scales that we've observed them so far, they don't repeat. So about 90% of them are these sort of loners. There are a few that repeat. There's a repeater that repeats on a roughly 16.5 day cycle. So it squirts out a pulse roughly every 16.5 days. So I'll talk a bit about dispersion. It's been talked about earlier today in a couple of different presentations, but basically any electromagnetic wave traveling through either the ISM or the IGM will become dispersed due to traveling through the plasma column or through the electron column, if you will. Shorter wavelengths arrive ahead of longer wavelengths. This is more or less what happens in optical fiber, and modern optical fibers have controlled dispersion, and they have optical processing techniques to get around it. So we use this thing called the dispersion measure to tell us about the distance to objects like pulsars and FRBs. Now, the distance estimates are just estimates based on a model that we've developed over time of sort of what the electron density is along any given line of sight. So it just gives us a very rough distance measure to objects. There can be things that can screw that up, unusual configurations of, plasma clouds and the electron column and so on. But the dispersion measure can be used as a first order approximation, as sort of a stand-in for the distance to a given object. So pulse-like wave structures will become smeared due to dispersion, which causes, if you're observing over a very large bandwidth, you probably won't see these pulses because they get smeared across your bandwidth and they get smeared below your detector noise floor, which is why we have to use techniques like de-dispersion and like synchronous detection to actually observe pulsars, most pulsars. You have to overlay pulses one on top of another to get enough of a signal to noise ratio that you can unambiguously identify that you've identified a pulsar. So for FRBs, you don't do synchronous detection because they're single pulses, but you still need to be aware of de-dispersion. So a lot of the techniques we develop for pulsar studies, because they do de-dispersion and so on, also apply reasonably well to FRB studies. Some of the tools aren't used or necessary just because of the single pulse nature, but many of the other tools are applicable from the pulsar world. So we talked about CHIME a little bit. It was built in 2015 for observations of redshifted hydrogen. They were looking and continue to look for signals from the epoch of reionization, and the antennas they're using are kind of ideal for that particular research. They are of sort of a modest frequency range between 400 and 800 megahertz, and they have access to a lot of the sky at any given time. So they have a very large field of view. 4 fixed parabolic cylinders, about 20 meters by 100 meters. There are 256 feeds per cylinder. They're dual polarization. And of course, it's all digital signal processing. The RF signals are digitized very, very early in the process. And then those digital signals are then distributed to the various experiments that need that data. Because they are operating for 400 megahertz to 800 megahertz, a lot of their data is very contaminated with RFI a significant amount of the time, which probably should surprise no one given the frequency range and the fact that they are in one way in the middle of nowhere, but in many other ways they're not. They're only like a 30-minute drive from Penticton in the mountains of British Columbia, and there's human civilization all around there, including a golf course right next to the observatory. So for a single cylinder, the field of view is about 1.5 degrees in the east-west direction and about 110 degrees in the north-south direction. And for the FRB project, it's arranged as 256 orthogonal beams. They use an FFT beamformer to do that. They detect approximately a few new FRBs per day, so like a handful of FRBs per day that are not already in the database. Oops, oh no, what did I do? Okay, sorry about that. The construction cost of CHIME itself was about $16 million, which is really a bargain given the sort of scientific value of this instrument. I don't know how much it costs to do the FRB add-ons, but the FRB experiment was an entire new trailer of digital processing equipment that they added later on after the thing was constructed. Oh, the other thing I want to note is that they have outrigger cylinders now. There's one that's built in a little tiny place that nobody's heard of called Allenby, which is about 100 kilometers from the main antennas. And there's 2 more outriggers going in the US to be not only just confirmation sites for CHIME, but also to allow much finer grained localization of the origin of these FRBs. So one is at Greenbank and the other is at Hat Creek, I believe. So the other observatory that we talked about a little bit was STARE-2, which is pretty much why I decided that an FRB search at an amateur scale may actually be something that's feasible. So it's 3 geographically separated telescopes. There's a single 21 centimeter feed at the apex of a 6-meter dish, not at the focus, at the apex. The dish is just there to act as a radiation shield. That's all it is. They're centered at 1420 megahertz with about 180 megahertz of instantaneous bandwidth. And they use time of arrival to localize the source. Single beam has a field of view of about 100 degrees because they're basically just using a naked feed. I think they might have a choke ring on it, but it basically has about 100 degree beam width. And so far, they've only detected this soft gamma ray repeater, 1935 plus 2154, which Wolfgang talked about later being detected as an FRB. It's on the edge of our galaxy, about 30,000 light years away. Their RF processing uses a Casper-based tool chain. That's one of the radio astronomy labs at Berkeley has a bunch of software and hardware tools that are used for radio astronomy in a lot of different observatories. And so their tool chain is based on the Casper hardware and software. So where do we come in? So I invented this concept called the simple, inexpensive FRB telescope, mostly driven by the fact that STARE-2 was successful, despite their very large beam width, which implies a very, very low sensitivity, and the fact that I was able to get my hands on some modest antennas, 3-meter antennas, last summer or the summer before for almost nothing. So we purchased 6 3-meter antennas, and we already had a bunch of 2.4-meter antennas lying around. We're centered at 21 centimeters because of RFI constraints, and we also had a lot of 21 centimeter equipment lying around. 15 megahertz of observing bandwidth at the moment, and that's largely just computational limits. We use GNU radio for an SDR-based signal processing chain. We have USRP receivers, but others can be used. HackRF, AirSpy, Lamy SDR, all of those things. This summer, we should be adding 1 or 2 more dishes at the Rideau Ferry site. And we just signed an agreement with an outfit that owns an ex-NATO satellite ground station site near Ottawa. And they don't use the antenna there. There's a 14-meter antenna there, and we are collaborating with them to restore it. for various radio astronomy applications, including some FRB observations. So our current software is up on GitHub. You can see the URL there. It's called FRB Hunter 2 because I had an earlier version that I wasn't happy with, so I replaced it with number 2. So there you can see the cluster of antennas. I like to refer to them as a bouquet, actually, like a bouquet of flowers. So there will be probably 2 more there this summer with different pointings. This yellow one that you can see is 2.4 meters, and it's the only one that's actually movable. All the other ones have fixed pointings, although they could be adjusted as you need, but they're fixed pointing. So they stare at the same declination all day long. So what I wanted to do was compare the sensitivity of our dishes to some of the other FRB observatories. And you can evaluate sensitivity along a number of dimensions. So first we look at the aperture-based sensitivity ratio between, for example, CHIME and one of our dishes. So CHIME, just based on aperture, is about 36:1. In favor of CHIME. STARE-2, on the other hand, is 1 to 400 in our favor. So then you look at the bandwidth link sensitivity. So sensitivity depends on a number of factors, including system noise, aperture, and bandwidth, and other things that may contribute to a loss of sensitivity, like problems in your system design, that sort of thing. So CHIME versus CCERA, the bandwidth link sensitivity, they have an 7-to-1 advantage. STARE-2 versus CCERA, they have about a 3-to-1 advantage. But if you aggregate these numbers together and you sort of multiply them out, our reception chain should still be, in a single beam, should be about 100 times more sensitive to events than STARE-2. So we should be able to detect events that are about 100 times weaker than what STARE-2 did along a single beam. Now, of course, then you have to evaluate field of view. So CHIME covers about 165 square degrees at any given moment. STARE-2 covers about 12,000 square degrees at any given moment. And our single dish covers, or sorry, our dish array covers about 100 square degrees at any given moment. And we're probably going to add another 50 square degrees this summer. Our estimate based on the postulated event rates for a STARE-2 type observatory is that we should be able to detect a handful of events per year that really are FRBs. So our processing chain, Wolfgang had talked about sort of the volume of the data involved. So we actually have similar limitations. So we observe on the sky for 10 to 20 minutes at a time. We create a Filterbank file, and Wolfgang will be very familiar with those. The output of the Filterbank is at about 12.5 kilohertz. So our time resolution is a little bit better than Wolfgang's, but our input bandwidth is narrower. So there you go. Then every 10 to 20 minutes, we grab this Filterbank file and we analyze the Filterbank file at a bunch of different delay slopes, which is equivalent to a bunch of different DM estimates. We analyze 2-second windows at a time, and we look for pulses that peak at some threshold sigma or signal to noise ratio above the background. And then once we have that, we apply some heuristics, make sure that our peak detection is at a meaningful DM. That is, if the peak in our Filterbank processing occurs at very low DMs, it's very likely not an FRB. It's very likely local. And if it makes it through that, we save those and do a bit of manual analysis offline. And then we just repeat that forever, all day long. We just do the same thing over and over and over again, looking for any candidate signals that sort of pass through the initial gauntlet of evaluation. And this loop has two different GNU radio flow graphs. One is the one that produces the filter bank, and it's relatively simple. It just receives the bandwidth, chops it up with a FFT-based filter, detects it, and produces a filter bank output. And then the other GNU radio flow graph is used in analyzing the delay estimate. So we repeatedly call the same flow graph on the same data, but with a different delay increment, looking for a single pulse that exceeds our SNR requirements. And then there's a shell script that goes around the whole thing to sort of orchestrate this. And it just runs all the time. Our dishes don't move. So we are basically in meridian transit mode, which is basically what CHIME does as well. They have a little sliver of the sky that the telescope looks at any given time. And the Earth quite handily rotates the sky through their field of view, doing the same thing at our observatory as well. So in terms of results, we haven't had any so far results that are unambiguously in FRB. We get every few days, we get something that kind of makes it through the first levels of filtering, and then I take a look at it and go, no, that's not an FRB. So back in March, we had one of these that looked like it might be an FRB. I mean, look at it. If you look at it in the time domain, and this is after dispersion, it actually looks kind of FRB-like. There's the main pulse here, and then there's this little thing here that already makes me scratch my head a little bit. But again, if it's from a magnetar, sometimes they produce a secondary or tertiary pulse. So maybe this was the real deal. Not sure. So you have to start looking at it in other dimensions and in other ways to convince yourself that it very likely is an FRB. Now, the DM for this one was already a little bit low. It was about 165 or so, which is consistent with the kind of DM that was expected or was observed from the STARE-2 object, that magnetar that was observed. So, but it's very low for extragalactic FRBs, which is where most of the FRBs have been observed so far. So it was already a bit suspicious because of the low DM. So, and there's a plot of the delay slope versus the SNR, and you can see that there's a peak at a delay slope of 5.5, which is just an internal number for us, which once you do all the math works out to about 165. And already because of that, there's, FRB origin hypothesis is extremely weak, but, we might as well go look through the data because it's a useful exercise, and you can only develop your analysis tooling once you know what it is you need to look for and what it is you need to reject. So that's what I've been doing. So it happened about 2 hours prior to sunset. So it could have been a solar radio burst, but the dispersion suggests otherwise. If it was a solar radio burst, it wouldn't have shown any dispersion at all. It could have been what they called a periton, which turned out at one of the Australian observatories to be the spin down of the magnetron in a microwave oven as they opened the door without actually turning it off. So that was the spin down time implied by the micro switch that's in the door that sort of emergency cuts off the magnetron. Our site does have a couple of houses within about 300 meters, so it could have been that. And like I said, we receive events at a couple every few days, which is much, much higher than you would expect for real FRBs. So the question becomes, how do you separate this wheat, from the chaff, or the chaff from the wheat? So we're going to establish a secondary site with matched pointings. initially just for one of our pointings, sort of the one that we think might produce the most results, far enough away to eliminate any common local events. So we're actually going to do two. There's that ex-NATO site that I talked about near Carp, Ontario, which is in the Ottawa area, basically. And there's a very strong additional possibility near Kingston. The person who runs the Kingston group of the Royal Astronomical Society has volunteered to set up a second site for us. So that will probably happen this summer as well. So if we take, if we look a bit deeper into the data, you know, how do we look closer? What is it we want to look at in the data to tell us whether it is or is not a possible FRB? So one of the things I added recently was that we look at the resulting pulse profile and we try to match it against Landau curves at a few different time scales. And a Landau curve is basically just a Gaussian with an extended tail, because some of these FRBs, when you look at them in detail, they look a little bit like a Gaussian with an extended tail. So Landau curve matches that reasonably well, and you can generate those automatically and then just do a correlation against the pulse that you have in front of you and one of the Landau curves at various time scales. So we did this with our putative FRB candidate, and the correlation coefficient was still 0.73, which is what you'd expect looking at the curve. It looks very much like a Gaussian with a bit of an extended tail. And if you look at the, this is the pulse zoomed in a bit, and with various curves there, the Landau curves that it was measured against, and then the correlation coefficients for the various curves. You can see the peak one is this dotted one, or this dashed one at 0.73. So, oh my, it kind of matches some of these curves. So is that enough to declare it an FRB? And I think the answer would be no, or maybe even hell no. It needs more analysis in multiple dimensions, despite already having passed through all of this gauntlet of trying to eliminate it as an FRB candidate. So then we go back to the filter bank and look at the individual channels and analyze the arrival times on each channel, which is basically what Wolfgang was showing with some of his visual plots, basically like waterfall plots. You could see that there was the pulse showed up, and it showed up with a nice dispersion curve. Although over those frequency range, it looks like a straight line. It's actually a very shallow curve because of the square law involved in dispersion versus frequency. So if we look at the individual channel data for that apparent FRB, any human will look at that and go, no, that's not an FRB. But it does show that some of the early techniques in the analysis can tend to fool you into thinking you're dealing with something that might be of cosmic origin when in fact you're not. Now, I'm not sure what the actual source of this was at the time, but you can see that it looks a little bit different on each channel. And once you smoosh those channels together with a delay operation between channels, you can easily see how they can all kind of add together to produce a very, very different looking, aggregate pulse. So each channel, if it really was an FRB, should look roughly similar. And this event that we saw is just a mess. I mean, it's clearly RFI, but of what kind, I don't know. And visually, when you look at the individual channel data, it just doesn't look like what you'd expect for an FRB. they're all very closely aligned in time overall, but when you apply a bunch of delays to it, because you are doing a delay and add, you can end up with this aggregate pulse that looks very, very different. And that event has all these discrete components, both in time and in frequency. So you end up with this impression that you have a dispersed pulse when in fact you don't, because it's clearly not meaningfully dispersed if you look at the edges of many of those features in the individual channels. And then if you look at the arrival time analysis against just an arbitrary, basically an arbitrary quadratic curve, it's much steeper than it actually would be in real life, but I plotted it here to just to kind of show what I'm talking about. So if it really was an FRB, the arrival times would more or less follow this red dashed line curve here, but in fact they weren't. The peaks in the individual channels were distributed, you know, so that somewhere around here, and there's a fall off either side. Definitely not an FRB. It's not showing dispersion like you'd expect from a cosmic object. So it's very, very, very likely terrestrial. And what this points to, and actually Wolfgang alluded to this, is that analysis of FRB data, particularly in the likely presence of RFI, is very complex and not entirely error-free, even when you're applying a bunch of different filtering operations to it. And we're going to pursue a machine learning-based approach, just as Wolfgang has, and CHIME does now as well. In the early days, they didn't. Now they do, because RFI can easily fool you. And so we're going to be doing the same thing. The confirmation sites will help a lot, because almost all of the RFI that you're going to receive at these frequencies is going to be relatively local. So sites that are, you know, tens of kilometers away, up to 100 kilometers away, if they're seeing the same thing, it's very, very likely coming from out there and not any kind of local terrestrial thing. Although in much lower frequencies, you can get things like lightning-induced pulses that will be seen over very large areas. But at 21 centimeters, that's really unlikely to happen. So our hope is that by combining AI approaches with confirmation sites, we should actually be able to eliminate a lot of the bogus detections that we're seeing at the moment. I mean, there are only a few, you know, per dish, you know, one or two every few days, but it still at the moment means I have to manually go and look at them and decide whether it's very likely something that's of human origin or not. And I would rather not have to do that. So we're probably going to head down the road of throwing some artificial intelligence at it. So the future is more dishes, more receivers, more analysis design work. We still have a few events that have to be evaluated deeper, but I very much doubt that they're actually FRBs. And of course, I mentioned our confirmation sites. So now I'm ready for questions. And I think I didn't even blow out my time window.
Know as you developed a high ratio of interesting comments to actual time classes. So I think you succeeded very well.
Oh,
thank you, Marcus.
Okay.
Well, thanks, Marcus. On this RFI thing, it's there's a very annoying type of RFI for us, and maybe you have something similar. Since a couple of months, we have somewhere in the vicinity or in the next area a frequency hopping radar. That's probably a military air surveillance radar or ATC radar. And what that does is it emits within a very short period of time a sequence of pulses on different frequencies, and they sort of jump around randomly in the frequency. And if you de-disperse such a signal, it can happen that de-dispersion just overlays the different pulses, and you get a nice signal, which at first glance looks like a dispersed signal. Of course, if you look at it closely, it has distinct frequencies that just happen to be overlapped due to the de-dispersion process. We can distinguish them by this artificial intelligence program by Fetch that does a good job on eliminating that. And it's quite possible that something along those lines is what is irritating your analysis there as well.
Yeah, it sounds like it. I'm not aware of such a radar near us, but that doesn't necessarily mean anything. Since if it's a military radar, we wouldn't necessarily be made aware of it. We're far enough away from the L-band surveillance radar that they operate at the Otto airport that we're likely not seeing that. I mean, the occasional aircraft reflection of that maybe, but again, it's frequency limited. It's not a wide frequency hopper. So it would be very unlikely for us to be seeing, for example, aircraft reflections of their L-band radar somehow desensing our front end. Yeah, it's kind of a mystery where some of these things are coming from, to be honest. It may be military and we would just never know. But as you mentioned, this needs a lot of sort of heuristics and a bit of artificial intelligence maybe to eliminate a bunch of things that would ordinarily require a human to look at it, and we'd really like to automate it, which is what CHIME has done and what you've done.
What about putting up a local antenna, like a slot antenna or something, on the same frequency, so that you're restricted somewhat to only stuff coming in terrestrially, and then trying to separate that out? You'd have to have a timing mark of some kind on both signals.
That could be an approach as well. We had thought about it. I just haven't had time to implement anything like that. But yeah, you're right. If we had like an antenna with a really broad field of view that was seeing some of the same pulse structures at the same time, then yeah, you could basically use that as like a radar blanker to just say, okay, while this is going on, none of our other observations are valid.
Thank you for your presentation, Marcus. Another great one. I'm here to learn from others. One of your bouquet of dishes is not like the others. It's rather yellow. Is that paint? Does it matter?
It is in fact paint, and when we were at our previous site, we tended to paint a lot of our mechanical infrastructure school bus yellow just because I happen to have some. And then we decided it was kind of like our color. And one day after I put up that 2.4 meter dish, I decided, what the heck, let's paint it yellow, bright yellow, because we had a lot of that paint around, just because it's fun and friendly. And then I think it was Gary suggested turning it into a smiley face. So that's what we did. At these frequencies, paint doesn't matter. It's just a very, very thin extra bit of dielectric, which your signal won't even notice, because the difference between its thickness and the wavelength you're dealing with is very, very large. So it basically just doesn't notice.
And is that a solid metal, or is it some kind of screen?
Oh, it's a mesh dish. It's a very standard, 2.4 meter satellite dish, like the big ugly dishes people used to have in their backyards.
Like my backyard. Thanks very much.
You're welcome.
The only thing you want to be careful with paint is that it's not reflecting infrared. Otherwise, you might
Oh, yeah.
burn
Oh,
burn
yes.
something, especially if it's a solid dish, and if you have
Yes.
infrared reflection, it can get pretty hot in the focal point.
I have a quick story about that. The solar radio telescope at DRAO, which they upgraded several years back, and of course it tracks the sun all day long, and it took them many iterations to find a paint that wouldn't reflect infrared back to the feed, and literally they lost 2 multi-$1,000 feeds because of the reflectivity of that dish. And because it tracks the sun all day long, it's going to be a huge problem. But they found a paint that was gray and had these little, like, it basically had sand in it, and it was gray, and it diffused the optical stuff just perfectly. And their mean temperatures at the feed went down by hundreds of degrees, kind of thing.
It'd be nice to know the name of a paint like that.
Yeah, I can probably actually get that the name of that paint and post it to the SARA list at some point.
That'd be great.